So this chapter 10 is electromagnetic induction. Electromagnetic induction is where they use magnet together with a conductor. The conductor has no current initially. No current initially. So they move the magnet into the conductor. Then at the end, the current is produced. Okay, so the EMF is induced. That means voltage is produced. Voltage is produced. So this is about electromagnetic induction. Electromagnetic induction, I have to put it in this way. We have magnet B, we have force to push the magnet into the coil, for example, and then it creates current. So for this case, magnet and force to the conductor, then it creates current. So this one we use Fleming right hand rule. Fleming's right hand rule. What we learned previously in chapter 9, right? So we have magnet, we have currents in the conductor. They both creates their own magnetic field, then they interact, then they create force. So in this case, we use Fleming's left hand rule. So this is the difference. Okay. So the chapter 9 situation is where we apply it in motor, for example, in motor, like fan. Okay, so we have magnetic field, we have current, then the fan is spinning, so that is the force. Okay, so this one we use it in generator, for example. Okay, let's say hydroelectric. So there is a magnet, and then the water is flowing through the turbine, turning or spinning the turbines, and then it generates electricity. So generator. Okay, so maybe I write down first. This one, the example is motor, as in fan. Okay, so this one, the example is generator, as in generator, hydroelectric, for example. Okay, now let's say how it works. Inducing EMF. EMF, in general we call it voltage. So inducing EMF, that means produce voltage. So first point, electromagnetic induction is an action at a distance phenomenon. Action at a distance, that means the magnet and the conductor or the coil is not touching each other. The magnet is approaching the conductor or the coil but not touching the coil, and at the end the current is produced. So they're not touching, so it's action at a distance, something like remote control or something like that. So the magnet and the conductor is not touching, but they can produce something. They can produce current. Now here, second point, EMF is induced when magnetic flux linking a conductor changes, either by the number of lines linking the magnetic field changes, or the number of field lines being cut change. Okay, so they are trying to tell us two situations where the EMF is induced. Okay, so how are we going to understand this? First, you have to know that the permanent magnet here create magnetic field. Okay, create magnetic field. So when they create magnetic field, so the magnetic field will cut the conductor. Okay, we'll cut the conductor. And you know, if we cut the conductor one time, it is not enough. You have to keep on making the magnetic field to cut the conductor. So that's why you have to keep moving, moving in and out. Okay, moving in and out. Move the magnets or move the coil in and out. So when you move the magnet in and out, for example, the coil is not moving. Okay, so let's say we keep the coil stationary and we move the magnet in and out. So imagine that this line, right, is keep cutting the conductor in different ways. Okay, so let's say for example, initially there are 3 points. There are 3 points that cut there are 3 magnetic force that cut the conductor, as you can see here. Okay, 3 points, 1 point, 2 point, 3 points. Okay, then after that, when the magnet is brought closer, or the coil is brought closer, for this case, as you can see, the arrow is like that. The arrow is like this, right? That means you bring the coil closer to the magnetic field, and then when it's nearer, the magnetic field is stronger. Then you can see more cutting. 1, 2, 3, 4, 5. Yeah, it cut at 5 points. So in that case, there is a change in the number of field lines being cut. So because of that, EMF is induced. So that's why you need to keep moving. Either you keep the magnet bar stationary and you move the coil. This is option 1. Or the second option is you keep the coil in stationary, but you keep moving your magnet. So that is option 2. So as long as there is a change in the way that they cut, okay, then they will have EMF induced. So the number of field lines being cut change by moving the magnet or by moving the coil. Okay, so let me write down first. This is by moving either the magnet or the coil. Okay, whereas this one, the first one, in what situation we have this? Number of lines linking magnetic field changes. Okay, so for example, you don't use permanent magnet, you use electromagnet. Electromagnet, the strength is affected by current, for example. Okay, so you increase the current of the electromagnet, and then the magnetic field is getting stronger. Then when it's stronger and stronger, the magnetic field lines is getting more and more. So there is a change in the magnetic field lines. So then the increase in the magnetic field lines, making the cutting of the coils changes, and that creates EMF or induced EMF. Okay, so example, increase the strength of electromagnet. That means you increase the B. Okay, so now example, moving coil from A to B. Okay, this one we discussed right there. So we look at the statement here. Number of lines linked increase from 3 to 5. So from 3 points that link, okay, the lines that link to the permanent magnet increase from 3 to 5. So you see 1, 2, 3. Now it's 5 already when you bring it nearer. Number of lines cut increase from 0 to 2. This one is like the increase of 2 units. Okay? Increase of 2 units. Okay? Hence, an EMF is induced. So there must be a change in the lines cut. Okay, now let's move on. 10.2. Okay, so we are having formula and terms over here. 10.2, magnetic flux linkage. Magnetic flux linkage. So you see they keep talking about link at the beginning. So you see like here, link. So just now on top also link. Okay, so then now linkage. What is that? So we look at the third point first. Magnetic flux linkage. Okay, magnetic flux linkage. Product of magnetic flux and number of turns. So number of turns, you should be able to imagine how many turns of the coil. Okay, how many turns of the coil? That is the number of turns. Magnetic flux is what? Maybe you still don't know yet. But here I just tell you first, it's phi lah, no? Phi. It's phi. Magnetic flux is phi. This is magnetic flux. Okay, write down. Magnetic flux is phi. So multiply with the number of turns of the coil, then you get magnetic flux linkage. You know the formula, but you don't know what is that, right? So we have to see later. So at least now you know the formula already. You know that magnetic flux linkage is N multiplied with phi. So what is magnetic flux? So let's see the first point. Okay, the first point. Magnetic flux, product of magnetic flux density. Magnetic flux density is something that we learned in the chapter 9. Magnetic flux density is B. So that time I said this is magnetic field strength. Magnetic field strength. Okay, so it is related to force actually. Okay, related to force. Okay, so where we have to know that magnetic flux density is force per unit current per unit length. Okay, so it's something like that. So it is related to force. Okay, so you know magnetic flux density already, and what they said here is product of magnetic flux density and area normal to the field through which the field is passing. Okay, so then they give us a formula. Okay, now let's understand it. Area normal to the field through which the field is passing. So what is area normal to the field? Okay, so for example, let's say you see this is the coil. So area normal to the field. Area normal to the field. Okay, you know the field is like horizontal. It's like going out like that, horizontal. Okay, area normal to the field is hence the area over here. The area normal to the field. Okay, it's that area. Okay, so we have to take area inside the coil. Okay, area inside the coil as the area that is normal to the field. Okay, let me write down. This is area inside the coil. Okay, so you take that area, which is this area, the blue one. Okay, so you take that area, multiply with the magnetic flux density, then you get magnetic flux. I get magnetic flux. So again, there's a problem. We know the formula now. We know something like this. We know magnetic flux where the symbol is phi. Phi equal to B multiplied with area, which is A. So phi equal to BA. We know the formula already. Phi equal to BA. Okay, so we know the formula, but maybe you feel like, oh, I know the formula, but I'm not sure where is my magnetic flux. I just know the formula is B times A. But what is that actually? So we take a look. We try to compare between B phi and magnetic flux linkage. So we have three things here. Okay, so we move on first. Next one, Weber. Weber is the flux that passes through an area of 1 meter square when the magnetic flux density is 1 Tesla. So they are talking about this formula. So as you can see, phi equal to BA. So phi 1 Weber. You see the unit is Weber. Magnetic flux density 1 Tesla. 1 Tesla multiply with 1 ampere. 1 ampere. Sorry, one. This is not. I thought it's current. Okay, 1 meter square area. 1 meter square. Okay, so in this situation, then you will get the meaning of 1 Weber. 1 Weber is when the magnetic flux density is 1 Tesla and the area perpendicular to it is 1 meter square. Then you get magnetic flux. Okay, so actually we learned magnetic flux last time in chapter 9. So that time when we learn magnetic flux, right? So it is written in the notes there saying that this is the number of magnetic field lines passing normally to a given area. So number of magnetic field lines passing normally to a given area. So that is the meaning of magnetic flux. Okay, how many field lines passing normally to a given area? So from here you know already. Okay, you know what is magnetic flux already. It's how many field lines passing through an area that is normal to it. Okay, now then what is magnetic flux density? I think this one you know already. How strong is the magnet? Okay, and the third thing is what is magnetic flux linkage then? Magnetic flux linkage. Okay, so linkage, you know lah, linkage is how much they are linked together. So magnetic flux linkage, right? Basically, we can put it in this way. We can say it, we can explain it as a magnetic field induce an EMF across a coil. Imagine that. You know, when you put magnetic field across a coil, right? So it induces an EMF. If the magnetic flux changes with time, try to imagine, you need to keep moving in and out, right? So then there is a change in magnetic flux. Change in magnetic flux. What is meant by change in magnetic flux? That means change in the number of lines. Magnetic flux is the number of lines, remember that. Okay, number of lines that pass through a particular area. So change in magnetic flux with time. So the magnetic flux which induces a current in the coil is known as the magnetic flux linkage. So that is magnetic flux linkage. What is that? Magnetic flux linkage is the magnetic flux which induce a current in the coil. Okay, so I write down in short for three of these. We have three things, right? So we have three things. The first one, magnetic flux is number of field lines passing normally to a given area. How many lines? You need to keep changing the lines, then it induce EMF or induce current. So you need to keep changing the line. So that is where we have the magnetic flux linkage. Okay, This is the magnetic flux which induces a current in the coil. Okay, so of course you want to induce current, right? You have to, if the magnetic flux changes with time, you have to keep moving the magnet, then the number of lines that passing through a given area is keep changing, then current is induced. This is called magnetic flux linkage. Okay, so that's why there is a link there. There must be a relationship between the magnet and the conductor where the number of field lines keep changing. Then that is magnetic flux linkage. Magnetic flux density is how strong is the magnet. This one is the previous chapter, so we don't want to focus too much on that now. Okay, so you may think of unit. I know the formula already. Magnetic flux linkage is equal to n times phi. N times phi. Okay, so n times phi. Then what is the unit? Logically, you should be able to think about the unit, because the unit of phi is Weber, and number of turns has no unit. So end up with magnetic flux linkage. The unit is Weber also. It's Weber. Yeah, it's Weber. So if you put phi with BA, right? So it will become NBA then. The formula become NBA, which should help you to remember. NBA, the basketball. Okay, so if I look at the formula, I think of something also like, since magnetic flux is the number of field lines that passing normally to a given area, then magnetic flux linkage you have to multiply with the number of turns in the coil. Okay, so that means magnetic flux linkage is like the total number of field lines after considering the total area. Each coil will have area also, so it's like the total number of lines. Okay, so that pass through the coil and creates current. So next one, factors affecting magnitude of induced EMF. So we have three factors here. The first one, magnetic field density. Magnetic flux density. Let's standardize the words. Okay, magnetic flux density. Okay, so which is B. The stronger the magnetic flux density, of course, the EMF induced will be greater. Imagine you're using a strong magnet to move in and out of the coil, then of course it will be stronger. The EMF induced will be greater. And then speeds of motion of the magnet, the V. Logically true, you move your permanent magnet in and out quickly, then you will induce more EMF. Number of turns of coil, logically this is true also, because if you put more turns, then it will increase the magnetic flux linkage. Magnetic flux linkage is the one that generates current. So if the N is greater, then the EMF induced will be greater also. Okay, so these are the factors that affect the EMF induced. Now let's move on. Okay, Faraday's and Lenz's law. So Faraday's law, the magnitude of induced EMF is proportional to rate of change of magnetic flux linkage. Magnetic flux linkage. So rate of change of magnetic flux linkage. That means how fast you change the number of lines. You know, from 3 lines being cut to 5 lines being cut, something like that. How fast you change that. Okay, so the faster you change it, the EMF induced will be greater. That is based on Faraday law. Okay, so the d n phi is the change in the magnetic flux linkage. As you know, n phi is magnetic flux linkage formula. The change in magnetic flux linkage over the change of time. Okay, over the change of time. So how fast you change it will affect the V, the EMF induced. Yeah, the EMF induced will affect the magnitude. Just the magnitude only, The Faraday law never talk about what direction is the EMF. They never talk about that. Faraday law just talk about if you move faster, if you move your magnet faster, then the V will be of greater value. What direction? Lenz's law tell us. So this one tell you the magnitude, this one tell you the direction. So Lenz's law, they say the direction of the induced EMF is such that it tends to oppose the flux change, causing it flux change. So that means how many lines is being cut, that is the flux change. Okay, so the main word here is oppose. It tends to oppose. Okay, how it oppose? Example, if you are using a south pole to enter the coil will try to oppose this movement by creating another south pole over here to oppose the motion. How it oppose? South and south, they will repel, right? So you want to enter, then it opposes you by creating south pole. And because of this south pole, then we can find out the direction of the current by using right hand grip rule, where right hand grip rule is where, okay, this is your right hand, so your forefinger have to turn this way, then your thumb will point there. So right hand grip rule. If you are wondering when should I use right hand grip rule again, cannot remember the theory, the concept, then here I tell you again. So when you have B and I, so then you can use right hand grip rule, B and I. Okay, that means for this case, I have B. I know here is South Pole, so I know B already. South Pole here, North Pole, North Pole. Yeah, North Pole is the other side. North Pole is where the magnetic field come up. So then your thumb have to point to the other side, point to the other side. Point from North Pole to the other side. Okay, so that's why your thumb is pointing there, and then the forefinger twist in this particular way, where the current have to follow the forefingers. So where the it is going down in front, the forefingers point in the way that is going down in front. So that means, you see, in front of the coil, the current is going down. At the back of the coil, the current is going up. So the forefinger determines the direction of the current. Okay, so that is oppose. Okay, so then that is Lenz's law. So another example, you know, your permanent magnet, right, in order to create EMF, so you have to move in and out, in and out. So at one particular moment, you are moving out. Yeah, when you are moving out, according to Lenz's law, they are trying to oppose you again. The coil will try to oppose the motion by avoiding the permanent magnet from going away. That is opposed. So to oppose this, they have to change the north pole now, so that it attract you and oppose you from going away. So when it changes to north pole, then you have to turn your right hand grip rule to the other side, so that your thumb is pointing to the left, and then the forefinger cannot see already because it's at the other side. Okay, so uh, the current will turn in the opposite way then. Okay, so your thumb is pointing from north to the other side. Okay, then your forefingers, which is in that way, meaning that the forefinger is going down at the back. It's going down at the back. It's going up in front and going down at the back. So you will see the direction of the current changes. So that means when you go in, the current flow up to down. When you go out, the current flow down to up. So this kind of current is called alternating current, which is keep changing in direction. Okay, alternating current. So that's why we have chapter 11, alternating current. Now let's move on. We see the formula first. Faraday law, no negative. Lenz's law, same formula with negative. So that means that means if you look at Faraday law alone, you are finding the magnitude of the voltage. So if you use Lenz's law, then you are finding the magnitude as well as the direction. The direction is just opposite direction. Yeah, it's opposite direction. So very important. The formula here is very important. They will tell us how the thing works. Okay, so I will go through some past paper after this page, and then from there you try to build up your Faraday law, Lenz's law, and exam techniques. Okay, now let's move on. Past year question. Use Faraday law to explain why there is a reading on the voltmeter. Okay, Faraday law. Faraday law, the law said about the rate of change of magnetic flux linkage. That means how fast you move your magnet and cut the coil, So you have to say it in that way, So that's why the answer. Moving magnet causes a change of flux linkage. Flux linkage. So what is flux linkage again? That is the number of magnetic field lines that is being cut, which causes the EMF to be induced. Okay, that is a change in the number of lines being cut. So you move the magnet, then there is a change in the number of magnetic field lines that is being cut. So which creates a reading on the voltmeter. So B. This reading varies in magnitude. So, according to Faraday law, right, the V is big if the rate is faster. The rate is greater. Yeah? If the rate is greater, the rate of the movement of the magnet is faster or greater in rate, then the V is greater. So speeds of magnet varies, so varying rates of change of flux. So okay, this and this is different. This one, the first one, right, A, right? In what situation it will have reading? If you move the magnet, it has reading. If you move it fast, then the reading will change quickly, will vary quickly. Okay. So C, the reading has both positive and negative values. So how? This is actually Lenz's law. Lenz's law, opposite direction. Because Faraday law explain magnitude only, never explain the direction, never explain the plus minus. Plus minus is Lenz's law. So uh, anyhow, we just answer it based on Lenz's law. Because you move your magnet in and out. Magnet changes direction of motion. Then based on Lenz's law, they are trying to oppose you. Then they change the pole of the coil. Then it uh, it makes the current flow in opposite directions. So that is Lenz's law. Okay. So now let's move on. Fleming's right hand rule. So again, same posture, and it's still FBI again. So the F is the force or the directions of motion. B is the magnet, okay, pointing out from north, and then current. Okay, so similar. Okay, now let's see the question here. A small rectangular coil ABCD contains 140 turns of wire. So I will label this as N first. How to use it, we don't know yet. Okay, now let's move on. The coil is held between the poles of a large magnet so that the coil can rotate about an axis through its center. So the axis is given here. This is the axis, the middle one. So it's rotating. So how it rotates? Two possible ways, either clockwise or anti-clockwise. So we don't know which way they are rotating. Okay, so when the current in the coil is 170 milliampere, how the current flow we don't know also. Okay, they don't put any arrow to show us, but two possible way. It's either here in and turn one round, and then here go up. This is the first possible way for the current to flow. The second way is the current go in from here, then come out after turning one round, then come out. So two possible way for the current to flow. Okay. The maximum torque, torque come in a sudden. So torque we learn in AS physics. Torque is force multiplied with the perpendicular distance. Produced in the coil is 2.1 times 10 to the power negative 3 Newton meter. So that gives us the maximum torque. Okay, so you have to know when is the maximum torque. So that's why they are testing you now. So A, they test you on this. They say what position to the magnetic field should the coil be in for maximum torque. Position of the coil. Okay, so how to answer this? First of all, we need to understand the different position of the torque. The different position of the coil. Sorry. Uh, as I mentioned just now, the coil may rotate clockwise or anti-clockwise. Okay, so but they don't tell us what direction is that, and we don't know it is clockwise or anti-clockwise. But it doesn't really matter one actually. So as long as we know it is rotating, which direction doesn't really affect the answer one. Whichever direction that you set here, it will end up with the same answer. Okay, so let's say I set a direction of the current. Okay, let's say the current go in from from here. The current go in. So then the current come out from here. So here they go in, and here they go out. So the current will go in here, and will go out here. Okay, so that means they turn one round, the current go in, turn one round, then come out. Okay, so that is the direction of the current in red color. Then the question never tell one, I simply set. Like what I said, it doesn't affect the answer. So I just set. And let's say I set again. Let's say I have the current now. Then I set, let's say here is North Pole. Okay, here is North Pole. And here is South Pole. Then I have my B already, I have my B. So for wire AB, I can use my, okay, now you have to determine, should I use Fleming left or Fleming right? You have to determine that also, Fleming left or Fleming right. So, Fleming left is Fleming left is B plus I become F. Fleming's right is B plus F to induce EMF or induce current. So you have to think whether the current is induced or the current is provided by the battery or by the power source. So you have to determine based on that, whether the current is induced because of the force or it is provided by the power source or the battery. Okay. So we look at the question. They say when the current in the coil is 170 milliampere, the maximum torque produced. This one is very important. The current is there first, then it turns. The current is there, then it turns. So that means Fleming left. The current is there, then it turns. That is the torque. Fleming left. So we have to use Fleming left. This is like the fan, You turn on the electricity, the current is there first, then the speed, the fan will turn later on. Okay, like fan. Okay, so Fleming left hand rule. Okay, I consider two parts because I have wire AB. And I have wire CD. So I have to consider separately because the current flow in different direction. So I have wire CD. Okay, so wire CD and wire AB. Okay, I use Fleming left hand rule. I write down my B. My B is to the right, north to south, right? So my current is this way. For wire AB, as you can see, they are going from A to B. Okay. So I use Fleming left hand rule now. I want to determine the force. So I know that the force is going down based on Fleming left hand rule. The force is going down. Okay, wire CD. Wire CD is where the current flow back. You may wondering, how about here? BC, the current flow this way. If the current is flowing in the same direction with the magnetic field, no force. BQV sine theta. The theta is 0. Okay, no force for BC. So here, perpendicular with the magnetic field, then there is force. Okay, so let's find out CD. The current is flowing from C to D. Okay, meaning that the current is flowing this way. The B is this way. Okay, so we need to find the, use Fleming left hand rule again to find the force. The force is upwards. Okay, so now I put the force in blue color in the diagram. Oops. Okay, so we don't want overlap. So I draw again here. The force is down, and here the force is up. Okay, so then what is torque then? You know, torque is the two forces that make the coil spin. The two forces are acting in opposite direction. Multiply with the perpendicular distance. Perpendicular distance I put in green color. Multiply with the perpendicular distance, the green color, which is obviously that is 2.8 cm. Is this maximum or not? Okay, so let's consider the different possible positions. As we have, as what we know now, we know the coil is spinning in anti-clockwise direction based on the force. As you see here, they are going down. Here they are going down, and here they are going up. So meaning that the coil is spinning this way. Okay, anti-clockwise direction. Okay, so the question is asking for position. So it is possible to have two important positions to consider. One is where the coil is flat. The second one is where the coil is in vertical. You know, it's spinning, right? So somehow it will become vertical at a particular moment. Okay. Now let's say it become vertical, CD, and the AB go down already. AB go down. Okay. So this one is AB, and then here CD. Okay. So let's consider these two. These two will be enough already to know which one is maximum torque. Okay. So your force is down. Here the force is up. The perpendicular distance is here to here. Perpendicular distance. We discussed this already. Okay, let's compare to this. The force is keep adding up for wire CD. Keep adding up. Keep adding up. Even when they are in between this and this, the force is still acting up. You know, the coil is keep rotating, right, in anti-clockwise direction. So the force is keep acting up all the way until here it's still acting up. Okay, so the force is still acting up when it's vertical. Okay, I purposely draw a line here. Now, this one, the force on wire AB is keep acting down, and all the way during the spinning in anti-clockwise direction until here it's still acting down. Okay, so the force is acting up, here the force is acting down. Now, torque is the distance between the two opposite force, the perpendicular distance between the two opposite force. So when it is in this vertical position, right, there is no distance, as you can see. The distance is in green color, right, for this case, when it's horizontal. Now there is no distance, I want to draw a perpendicular lines. I want to draw a horizontal line between these two forces, but can't because there is no distance. Two of them are just having zero distance from each other when they are in this way. So because of that, torque equal to force times D. Yeah? Force equal to torque times D. So the torque is maximum when it is like this, when it is in horizontal. Okay? But when it is in vertical, the torque is zero. The torque is zero because no horizontal distance. Okay? Maybe I put one more example. When they are halfway between horizontal and vertical, how is the situation? Let's say halfway in between. Okay, let's say I try to imagine how to draw this. Let's say your CD is here. Your CD is here. Your AB is down a bit. Okay, to make it parallel. Okay, this is where it is in between. In between, it turned a little bit already. Okay, it turned a little bit already. So let's see how is the force. So again, I label it. This is my CD. This is my AB. It turned a little bit already. Okay, so the force is upwards. This one is downward. The perpendicular distance, right, is this one, the green one. Okay, of course this is smaller lah. This is smaller. This is going to be smaller. It's just that my diagram looks a bit not proportional, not in the correct scale. Okay, to show that it's shorter, it's better to change it a little bit so that you don't misunderstand. So when they are in between, we need to measure the force in that way. It will be shorter. The distance will be shorter. Okay, the distance will be shorter. So maximum happens here. The distance will be 2.8. When they turn halfway, the distance will be smaller than 2.8. As you have to imagine on that. When it's vertical, the distance is zero. The distance is here, then getting smaller and smaller until it becomes zero. It is zero when it is vertical. Okay. Now, how to answer this question then? We know maximum is here. They ask for position. So, how to say out this position? Okay. So the position is when the coil is in horizontal position. The other way to say the position is in parallel plane with the magnetic field. This is the other way to say out the position, which is this situation. Now we look at B then. For the coil in position shown, calculate the magnitude of the force on side AB. So we want to count the force. Okay. So how to count it? Or what formula should we use? Okay. In this position, right, F equal to BIL sine theta. the theta is 90. As you can see, it is perpendicular. The current and the B is perpendicular. So we can just use F equal to BIL because sine 90 is 1. Okay, so the problem is we don't have B. We don't have B. We have I. We have L. Okay, so we don't have B. So we have to use different way. So this formula is not applicable for temporarily. Okay, so I hold it first because B is unknown. Okay, so what to do is let's consider another possible formula. Let's use torque formula. Torque equal to force times perpendicular distance. So the torque is 2.1 times 10 minus 3. The force will be the same, just for your information. The force on AB or CD will be the same value. So they ask for the force on the side of AB. No different. The force on CD will be that value also. Okay, distance is 2.8 cm. So this is the distance, 2.8 cm. 2.8 times 10 minus 2. Convert the cm to meter. Okay, then you will get force equal to 0.075 Newton. Okay, so we get the force ready. Now part C. Show that the magnetic flux density B is 70 millitesla. Okay, so this one we have to be careful a bit. Okay, we have to be careful to get B, right? Okay, let's say I put the answer here. Part C. Okay, first of all, we need to know that this force is the force on AB. It's the force on AB, and then this force is created because of the magnetic flux linkage. Or maybe I should say it. This force is created because of the interaction between the B and the I. The interaction between the magnetic field, it creates the force, and then there are many turns of coil over there, and that is what am I trying to say. There are many turns of the coil there. So based on the question, there are 140 turns, as you can see, 140 turns. Okay, so 140 turns over there. And our formula, F equal to BIL, which is the possible formula to find B, right? Okay, F equal to BIL. So this formula is suitable to be used when it is one turn. When it is one turn. Okay, when it is one turn. Okay, when it is one turn. So I write down first. F equal to BIL. This is for one turn of coil. It's for one turn of coil. Now you have 140 turns, 140 turns. The forces created is this value. The forces created is this value. So this value is because of 140 turns. Okay, so we had to work out accordingly. So which means which means for 140 turns, we have to time 140 then. Okay, hold on. Okay, now let's continue. So F equal to BIL is used for 1 turn of coil. So if there are 140 turns of coil, right? So the forces created is 0.075 Newton. Okay, you know, each turn will create a particular value of force. So now 140 turns create this. Okay, so I write down here first. This is the force due to 140 turns of coil. 140 turns of coil. So the formula here is for 1 turns of coil. Okay, so to find out the force for 1 turns of coil, we take 0.075 over 140. The B is what we need to show, 70 millitesla. The current is 170 milliampere. 170 times 10 negative 3. And then the length you have to remember, the length must be the length inside the magnetic field, which is the length of AB, AB, 4.5 cm. 4.5 cm. Don't take the length of BC. Okay, take the length of AB. 4.5 must be perpendicular to the magnetic field. Okay, then after that you count the B, bring all the values to the other side and divide. Then you will get B equal to 0.070 Tesla, which is 70 millitesla. Okay, so we managed to show it. And then part D, the current in the coil is switched off, and the coil is turned through an angle of 90 degrees in a time of 0.14 seconds. Calculate the average EMF induced. Now this is Fleming right hand rule already, at this point onwards, part D, because they turn off the current, but the coil is still spinning, imagine that the coil is still spinning, so there are force, magnetic force is still there, force is still there because it's still spinning, and then it induced EMF or current is produced, and they give information. It takes 0.14 seconds to move 90 degrees. Calculate the average EMF induced. Okay, so you have to calculate the EMF induced. So EMF induced, use Faraday Law. Okay, so V equal to D N phi over dt. D N B A over dt. Okay, so N 140, the number of turns of the coil, magnetic field 70 milliampere. So 0.07. This is a B. A. This A must be area perpendicular. Area perpendicular to the magnetic field. So when it's 90 degrees, the area will be this area then. It's 90 degree. The area will be this area. So the one that I put in green color, so it's that area. You know, it turns 90 degree, right? So it will be that area there. So which is 2.8 cm times 4.5 cm. So 2.8 times 10 minus 2. 4.5 times 10 minus 2 over time. The time is 0.14. Okay, then we have to check answer by multiply all this. Okay, 0.070, 2.8 times 10 minus 2, 4.5 times 10 minus 2, equals 0.14. Okay, so we get 0.0882 volt. So that is the Faraday law. Okay, so settle for this. Okay, so two coils P and Q are placed close to one another, as shown in figure 10.1. So part A, the current in coil P is constant. So there is a power supply. Power supply, so this coil P act as electromagnet. So this one produce B. So this one produce magnetic field because of the current, and it is electromagnet and produce B. Then this one, you see they connect to voltmeter. If they connect to voltmeter, so we should expect this is EMF induced. EMF induced here. Okay. The current in coil P is constant. An iron rod is inserted into coil P. You put an soft iron rod inside. So then the B will increase. Okay, so this action will increase the B. You know, the magnetic field will become stronger. Okay, explain why during the time that the rod is moving, there is a reading on the voltmeter connected to coil Q. So because, you know, when you put a soft iron rod inside, so the B is getting stronger and stronger, then the magnetic flux linkage is getting higher and higher. So that means the number of lines being cut is getting greater and greater. So EMF induced is getting greater and greater also. So we need to write it down. Insert iron rod changes magnetic flux density. The B that means. The change of magnetic flux in coil Q causes induced EMF. Okay, so this is consider nothing special. Okay, now let's move on to the other side. Part B. The current in coil P is now varied as shown in figure 10.2. So you see, you increase the current. Increase the current, increase the B. Increase the B. Okay, increase the B, the electromagnet. Okay, then after that, the current decrease, and then same. Okay, so on figure 10.3, show the variations with time of the reading of the voltmeter connected to coil Q for time t equal to 0 to time t equal to t2. Okay, you have to draw the EMF induced. EMF induced. So EMF induced, based on Faraday Law, it is V equal to d n phi over dt. And based on Lenz's law, that is a negative. If you are going to care about the direction, there's a negative. Okay, so, and after that, the other thing is the phi is BA, so it becomes NBA over dt based on Lenz's law. Okay, so what we need to know about this is EMF is induced. EMF is induced when there is a change in the magnetic flux density. So this is the change in magnetic flux density. Okay, then EMF is induced. Here is a change in magnetic flux density also. Then EMF is induced. Here there is no change in current. Then there is no change in magnetic flux density. So when there's no change in magnetic flux density, then no EMF is induced. Okay, so here, no EMF induced. Okay, so only here and here. So how? My suggestion, right? You remember it in this way, lah. You take it as, this is like differentiation, right? So you take it as gradient. Take it as gradient, right? So here to here is a positive gradient. Okay, that means imagine this is a positive gradient. Here to here, 0 to this point is positive gradient. Positive gradient, so the differentiation will be positive because differentiation is just gradient, right? So with another negative there, so at the end, the V should be a negative value. Okay, so let's put it here. Okay, negative. What value, don't know lah, okay? But no need to care one actually. So just draw a horizontal line. Okay, so we draw a horizontal line. Now, here to here, the gradient is negative. So imagine when this thing is negative, then there is another negative in front to make it to positive. Okay, so at the end, the V should be positive then. So here to here, this is a little bit after the T1 already. A little bit after. Okay, so my line is not vertical. Okay, a little bit after T1, the gradient is negative, then negative, it becomes positive. The gradient is greater, you see it's very steep. Very steep. This one not so steep. The front part, the first part of the graph is not so steep. Then the EMF induced is smaller. If the gradient is very, very steep, then the induced EMF has to be greater. So you have to make it to be greater. Okay, after that, this part onwards, there's no change in current, no gradient, no EMF. So we draw a horizontal line. Okay, so that's the graph. Okay, so my suggestion, you look at the gradient. The gradients will determine the EMF induced. Okay, I just tell verbally lah. If let's say I give another example, if my I versus T, I versus T is like this. If my I versus T is like this, then how is my E versus the EMF induced versus T? Okay, so similar. When it is flat, no gradient, and then no gradient, no EMF. So that part is flat. So this part, you see the graph is going down, negative gradient, negative gradient. So after that, you know, when it's negative, right, there is another negative based on Lenz's law to make it to positive. Okay, so it is same negative gradient all the way until here. So that means when we draw from this, when we draw from here to here, so it's negative gradient, right? So we'll end up with, you know, because of the other negative, it will end up with positive. After that, this part, no gradient, no gradient, no EMF. So it should be flat. Should be flat here. Okay, until here. Okay, now from this part onwards, there is a positive gradient. Positive gradient, positive, then with the negative in front, as you can see on the Lenz's law formula up here. Okay, when this is positive, here is negative, so end up with negative. Okay, so that means all the way here, so it should be negative value. And after that, so this part, okay, this part is where it has no gradient, no gradient, no EMF induced. So this is the exam technique that you need to build up, especially in terms of graph. So the gradient represent the EMF induced. So you have to remember that. Okay, so this is one of the past year question actually. So I just quickly put the important part here and discuss with you. Okay, so settle.